Hi everybody, and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and now we'll be going over the Kahoot for Lecture 6, moving to the physical domain. So, question 1 of 9. When do we create our floor plan? Note, disregard topographical synthesis. After writing RTL and before synthesis, after synthesis and before placement, after placement and before clock tree synthesis, after clock tree synthesis and before routing. Well, we're at this stage in our lectures, so let's choose this one. And indeed that's the case. So we'll go over to our lectures and we'll see that in our design we did our definition and planning, then we did our design verification, and then we ran our logic synthesis. Now we're moving over to the physical design. Okay, the physical design is going to have placement, routing, and so forth. But before we actually place our things, we have to draw up our floor plan. So our floor plan is going to be achieved after synthesis and before placement. We'll see the other stages in further lectures. Question 2. Which of the following do we define when moving from synthesis to floor planning? Global nets, cell abstracts, physical cells, or all of the above? Well, I guess we're going to choose all of the above. And again, let's go over to our slides and we'll see what we're talking about. So during synthesis, our worldview was a bit idealistic. We didn't have power supplies, we didn't care about physical connections, and we didn't care about clock idealities. To start the physical implementation, what do we need to do? We need to define our global nets. That means what we call our VDD and our ground and so forth. And we have to say how VDD connects to standard cells, how VDD connects to different macros, etc. We have to provide the left files, the technology rules, and the cell abstracts. And we need to provide physical cells that didn't have any libs because they don't have any functionality. Things like tie cells, decaps, filler cells, and so forth, which don't have any logical functionality. We also have to define hold constraints and so forth, and low power definitions like these types of multiple voltage domains and so forth. So going back here, global nets, again, that was our definition of, the names that we give our top level nets and how they connect to our standard cells and our macros and so forth. So say we have a global net called VDD, one called ground, etc., etc. Cell abstracts, those are the lefts of our cells. And physical cells, those are the filler cells and decaps and so forth and so on. Question 3. The following floor plan is, and we see a picture of the floor plan here. Is it core limited? Is it pad limited? Is it an IO ring? Or is it too dense to converge? Well, I remember that one is what we call core limited. Okay, so let's go back to our slides, and we see here that we have two basic types, I guess you could say, of chips. We have what we call a core limited. This would be the type of chip we want to have, that we only pay for silicon real estate that we really need, and then we fill it up with as many macros or as many logical cells and so forth as we need, and we get the IOs that are around here for free in that way. I mean, the number of IOs that we need are not what's limiting the size of our chip, but in many chips, sometimes in most of them, we need so many connections outside that just to put all these IOs, which are very big, okay, they're much heavier than the actual core area that we need, and that would bring us to a pad limited design. Often in today's type of chips, we would fill up the inside with extra memory if we had the extra space, because we're paying for the silicon real estate anyway. So this is a core limited chip, of course. It is not pad limited. An IO ring, well, it is an IO ring. This is the IO ring around it, but that's not what we meant here. And too dense to converge, it may be too dense to converge, but we don't have that type of data from this picture. Question number 4. What is utilization? The ratio of the core area versus the IO area of a chip, the percentage of the core area taken up by standard cells, the percentage of the chip covered by routing, or the percentage of routing tracks used. Well, utilization is basically this, the percentage of the core area taken up by standard cells. And let's see where that was defined. So utilization refers to the percentage of core area that is taken up by standard cells. And if we look at these two types of floor plans, this has a really high utilization. Most of the area is taken up by standard cells. There are very few of these little black areas. Most of them are covered by this blue type of a shaded area. Here we have a lot more black area, so it's a lower utilization. We actually set the utilization prior to floor planning. So we know how much our standard cell area is going to be because we synthesize the design. We have a net list. We basically have a Lego box that's full of all of these standard cells sitting here on the side scattered around. So we can go and we can sum up all the sizes of all the standard cells and know what our expected area of the standard cells is. Yes, we are going to upsize some cells, downsize other cells. We're going to add clock buffers. We're going to add some other stuff inside. But in the end, it's going to be pretty close, up to a certain number of a certain percentage of what we started with. So we get at least an order of magnitude. So the utilization is like the area of the box that we have around here divided, or the area of the standard cells that we just figured out divided by the area of the box that we put around here. And why is it not going to be 100%? Well, at the end, it is going to be 100% because we're going to fill everything up with fillers. But before that, we want to leave space for, number one, as I said, upsizing cells. We want to make a cell bigger, but if we have 100% utilization, we won't have any wiggle room. We need to insert a clock tree, so to stick in buffers and so forth. We need to do all kinds of other optimizations that may need to clone things and insert buffer trees and who knows what. But another thing and a pretty important thing is that we have routing congestion. So if we take a standard cell like an inverter that just has an A and a Y pin, and maybe it's even a big inverter with like a big driver at the end, it's going to be a big rectangle over here with two pins that has to connect to on its metal 1 connection. However, if we take something like a MUX, say a 4-input MUX, we're going to have 4 inputs, 2 selector inputs, and 1 output. And that means we have 7 pins on the area of just one standard cell, which may not be that huge. That means we have to come with a lot of metal 1 layers to connect to the standard cell itself, and that means high pin density. It's going to cause a lot of routing congestion in that area. We should have some wiggle room where we won't have any standard cells, that we will have 0 pin density around, so we can route around there. So utilization and routing congestion are very, very much tied to each other, as we'll see later on in further lectures. So our next question is, why do we need to uniquify the list? To make the Verilog correct, to enable the place and route tool to rename instances, to correctly propagate the clock to each instance, or to enable independent optimization of each instance. What a strange word, uniquify. Well, what is it going to be? I guess we'll try to enable independent optimization of each instance. So, unification may be a word that was made up by us VLSI designers. I'm not exactly sure. But it goes for the ability to really optimize each instance by itself. So when we write any type of software or something like that, we're going to use functions or procedures. We want to do to have reuse of code. So we're going to write our function in one place and then call it several times from some sort of higher level in our hierarchy. Call functions. The same thing is what we did with RTL. We're going to define some sort of a module, and then we're going to make instances of the module and use as many instances as we need, but use the same instance. So we designed and verified that module once, and then we can reuse it many times. And that's really good for designing our RTL, simulating it. It makes our code size smaller. It makes everything much more simple. The problem is that when we go into the physical domain, we get something like this. So we have this module, the B module over here, that has 2 instantiations of the A module. Okay, one of them is called M1, one of them is called M2, and they both have an inverter inside them. That's what the A module has, or a buffer, inside them. The problem is that, let's say we have this buffer has a large fan out, and so we need to increase its size. So what we're going to do is we're going to increase the size of this guy, but since they're the same, this is also going to increase, and that's not good. So what we want to do is, before we start our physical design, we want to blow this up into 2 separate modules. So what we're going to have here now is we're going to have B module, and then we're going to have two A modules, A module 1 and A module 2. And then when we upsize, the buffer inside A module 1, it's not going to affect the buffer that's inside A module 2. Yes, it makes our net list much longer, but that's just a bunch of text. And it works well that way. So that's what uniquifying is, and you have to do it before going to the physical domain. So, question number 6. Mark the incorrect guideline for a good floor plan. Prefer a single large core area, put RAMs in the middle of the floor plan, move pins away from the chip corner and narrow channels, or avoid routing around hard macro corners. Which one is not good? Well, having looked at a lot of floor plans, I'm going to guess it's the blue one over here. So, let's go back and look at some of the guidelines for a big floor plan. And this is a bit of hand waving, but it comes after a lot of years of experience of people who have made these types of floor plans and see what works. So we're going to always prefer a single large core area. And we'll see in the next lecture how placement algorithms work, and we'll understand that quite a lot. Okay. One of the things that's really important is that all of these macros, which are mainly RAMs, I mean, we have lots and lots of RAMs, but we'll have some other macros like the PLL over here and so forth. We want to get them out of the way. They have layers that are blocked up to metal 4 or even higher than that, which we can't route through. So when we need to connect, one standard cell to another, we don't want to have to go over such a thing as a RAM. So we want to push them out of the way. We want to push them to the corners, to the sides and the edges of the chips. With that being said, we need to leave routing channels that enable us to move, our routes as much as possible. These things also, unfortunately, they have a lot of pins that we need to connect to, so we still need to route to them. So we must leave big enough routing channels. Okay, and for that, we don't want to make constrictive channels, something like this. We put a bunch of RAMs over here, we put a RAM over here. We made this really bad area where we cannot route this way, we cannot route this way. We have to go through, and we don't have diagonal routes. So this is going to be really constrictive. It's a lot of area where you have to probably, move different signals between, this side and this side. So we don't want to do that. Avoid many pins in the narrow channel. So this is a kind of a problematic thing. We have all these pins here that are right next to the edge. It's going to be hard to connect to. So in older processes, what we could do is we could rotate this. Most of the time in newer processes, you can't rotate the transistors, so we're not going to be able to do that. So what we're just going to have to do is move this RAM away from the corner a bit to allow, access to the pins and so forth. Okay, and we should also put blockage. So these green things around there, like halos, that say, don't put any standard cells around here. Again, we want to reduce the pin density so we don't have to do routes to pins of standard cells. So we're going to put placement blockage around here. Don't put any standard cells here. Leave this whole area for routing. Okay, so those are the types of things that we're going to do. Move the pins away from corners. That's another one. So back to our Kahoot, we said prefer a single large core area, and this is something we really want to do. It'll help us get a much better result for our placement. Move pins away from the chip corner and narrow channels. Again, it's going to be hard to access those pins that are next to the corner or in narrow channels, and avoid routing around hard macro corners. So the corner is going to take up, one side of the routing, so we're going to have to only use the other side, and it's going to cause congestion. On the other hand, put RAMs in the middle of the floor plan. They're going to bother us the most there, so try to get them away from the middle of the floor plan. Okay, question number 7. What is an ILM used for? What is an ILM? Defining timing constraints on the I/O ring, feeding back floor plan data to topographical synthesis, simplifying and speeding up hierarchical design, or automating the floor plan generation. Well, think about that for a second, and I know the rest of them are just not true. It's for simplifying and speeding up hierarchical design. So let's see what an ILM is in general and what we need it for. So we said in the lecture and in the lecture before that in the previous Kahoot that we have a scope of our design. So if this is our design, right, our scope is our what's inside. We know everything about the reg to reg. So this type of a path, we know, the clock, how it goes to here and how it goes to here. We can figure out the skew between these two registers. We know where this register is. We know what the logic is in between this. This is all entirely encapsulated inside our design, and we can optimize it perfectly and so forth. Our problems come a lot of times when we look at the input-output right? The IOs. So here we have this B as an input to the design, and we don't know what happens outside, and we need to model it. Here, this Y is an output from the design. We don't know what's here, and we need to model it. Here, both A and Y, A is an input and X is an output, and we don't know what happens from whatever place that the signal initiates to whatever place it ends. We don't have a start point or an end point to these paths. So we need to model them. And one of the nice ways to do that is to use an ILM. Okay, so beforehand we talked about set input delays and setting the input transition or the driving cell, and setting output delays and the output load as a model for what we want to do. But those were kind of just hand waving and trying to make something up that would work, or timing, budgeting, and saying we have some sort of max delay to all the inputs and from all the inputs and to all the outputs. What we should do if we have a hierarchical design, someone else on our team is actually designing the block that's out here. Okay, we have the data of what's going on in our input delay, so let's give it to him. He has the data of what he's doing on his output, so let's give it to us and use it for our static timing. The problem is that all of this in the middle is, millions and millions or whatever, hundreds of thousands of gates is going to be a big mess, and it's going to be hard to run static timing analysis, take a lot of time and so forth, when it's irrelevant, right? So when I want to go and tell my neighbor who's making his block what my IOs are, I don't need to tell him about all the intermediate in the middle stuff, right? So I can just rip it out, and I create what we call an interface logic module. Model, which means that I ripped out all of my reg to reg paths and gave them only my interreg, reg to out, and into out paths, and they can see this whole thing. And then I don't have a made up model. I have the real clock tree. I have the real delays that are going on inside here, and I can really do full static timing analysis on the other block. I don't have to do all kinds of modeling, wrong modeling of the other side. Okay, so going to the next question, number 8. What causes electromigration, and what is electromigration in general? High resistance from the power source to the gate, defects in manufacturing of metal line or via, high currents flowing through small inductors over time, or diffusion of copper into silicon dioxide of dielectrics. Well, I think it's high currents flowing through small inductors over time. Okay, so let's see what that is. So electromigration, what we said, is a physical phenomenon. It's a reliability issue, and it happens all the time. The fact is that our conductors, our metal lines, they're made up of atoms, of copper atoms in this case, or previously aluminum atoms, and we have current flowing through. Those are electrons, that are flowing through these things at high speeds. The electrons are much smaller than the atoms of the wires, but they still do have mass, and they still are hitting the atoms. And there is a probability, or that after a while, the atom will move. And if I move enough atoms, I would say it's similar to a river running through, rock, water that comes down and runs through rock, and in the end it becomes a river. So when the enough electrons hit the atoms, they're going to cause them to move and eventually cause, a break in the wire. And that's an open circuit, or it could be a hillock where it actually, pushes some of the metal through the dielectric and touches another line, and that would be a short. So this is a reliability problem that is going to happen eventually, and our job is to make sure that it doesn't happen in the lifetime of the chip. It doesn't happen anytime soon. So why does it happen? It happens because we have high current density through a conductor. That means whatever the current is that we need to use by the gates, is going through a wire that doesn't have a huge, it doesn't have a huge area that it's flowing through. So we need to make bigger, fatter wires to provide the needed current. Now, in the past, electromigration was basically only checked on power rails because, what we're doing basically is we're filling up and discharging capacitors from VDD through a transistor to a net, and then from the net through the transistor to ground. And that means that we have current always flowing through VDD and ground. But on the signal wires, in MOSFETs at least, in CMOS, we're driving a capacitor, so it doesn't keep on flowing through. It fills up the capacitor and stops flowing. There's not this huge current flowing on signals all the time, and that's why we used to only check electromigration on our power and ground rails. However, because we've done such heavy wire scaling and the wires really have high current density, now we also have to run signal EM, which is actually running electromigration checks on the signals themselves. So going back to our Kahoot, is electromigration caused by high resistance from the power source to the gate? No, that's what we call IR drop. Okay. Defects in manufacturing a metal line or via. Well, electromigration causes a defect, but not in manufacturing. It's rather caused because of a reliability problem. And diffusion of copper into silicon dioxide dielectrics. No, that is a problem. Copper and silicon don't go well together. They diffuse into each other, and that's why it took a long time to get copper interconnect into our chips. But that is not what has to do with electromigration. In fact, copper is very good against electromigration, and it's one of the reasons that it was important to go from aluminum, which is really bad, to copper. Copper has a higher resilience to electromigration. What electromigration is high currents flowing through small inductors over time. Okay, that'll lead us to our last question, and Shima is really keeping a lead on me. So, question number 9. What are the goals of a power distribution network? To minimize static IR drop, to minimize dynamic DI to DT drop, to prevent electromigration problems, or all of the above. And I don't think you'd be surprised that it's all of the above. Okay, so let's go and look at that, a power distribution network. So we see that basically we have a gate over here, right? And a gate over here that's driving it. We have our power source, our VDD, and our ground source over here. And there is some resistance that we have to go through to get to the VDD of the gate. There is some resistance that is between the ground source and the ground of the gate. And because there's resistance and we drive current into here to fill the capacitor, and we drive current down there to discharge the capacitor, or all the capacitors that are, all of these gates that are in parallel, then what happens is we have some sort of a voltage drop over this resistance and this resistance, which causes the fact that we don't get VDD and ground at our gate. We get VDD minus something for the power and 0 plus something for the ground. And that is called IR drop. So I, which is current, times R, which is resistance, equals voltage, and we get a voltage drop over here. And that's really bad. And the way that we are going to solve that is by giving a power distribution network. So if we had our rails of VDD and ground, which cause our rows, which would be these horizontal pieces, what we're going to be actually doing now, that's a long wire, and if we need to get into a gate in the middle, it's a thin wire. We're going to have a lot of IR drops. So instead, we're going to add, straps, usually making a power grid in higher layers, bigger metals, wider metals, to provide connections to the power and ground supply that are basically closer, or to effectively lower our resistance or make the width of our conductor from the power supply to the gate itself much, much, much wider, thereby lowering the resistance. All those things that I said are basically equivalent. Okay, so that's to reduce IR drop. So that's the main goal, I would say, of our power distribution network, to have less IR drop. But also we have this thing that is dynamic IR drop. A dynamic voltage drop. So we have V equals L di to dt, and the thing is that these are rather constant, you would say. You have some sort of average current, and that's fine. Our inductance knows how to, the inductance over our whole chip that's caused by these loops, it knows how to hold this constant current. But the thing that happens with chips is, with digital chips at least, is every time we have a rising edge of a clock, we start a whole bunch of, these operations, of these toggling operations, which cause a spike in the current drawn out of VDD, or current drawn to ground at one point, and then it settles down. So that's a very non-kind of average. It's kind of it's all kinds of changes in our current, and and inductors don't like that. So what we're going to have is this problem with dynamic drop. Our voltage is going to drop over the power distribution network due to that. And so what we want to do is make wider wires that'll make our dynamic IR drop also be better. And of course, the less electromigration. So those three things are really the reasons that we're going to use lots of power lines, wide power lines. That's a point of our power distribution network. So that was actually it for this Kahoot. And if you want to ask me any questions, feel free. I'm available on my YouTube channel. Let's see, did I win in the end? Yes, I came in second place, even though I got everything right. It seems that due to the speed of Shima, he or she was able to beat me out. All right, bye-bye.